Good morning. Let's continue chapter 16 by talking about Henry's law. Henry's law is about dissolving gases inside the fluid. Let's say I have some fluid here, and then I try to push gas like oxygen and dissolve in this fluid. How much of this oxygen can I dissolve this in fluid? Well, Henry said it depends on two things. One is, what is the pressure that you are using to force this oxygen to dissolve? The more you use force, the more oxygen you can dissolve. And the second is the nature of oxygen. Is oxygen a soluble gas? The solubility of the oxygen also is going to make a difference. If this one is a very soluble, with low pressure you can dissolve more. If oxygen is less soluble, then you have to use more pressure. So therefore, Henry said, to find out the concentration of dissolved gas, how much we can dissolve a gas in the fluid, we have to look at the partial pressure of gas, px, also the solubility. For instance, we know that carbon dioxide is the most soluble gas in the air. Nitrogen practically is insoluble. Oxygen has solubility 1/20th of carbon dioxide. Now let me give you an example that you understand. If you do a scuba diving and you dive inside the water, as you go down, the pressure is going to increase. When the pressure increases, the air that you're breathing through the tank has nitrogen. As a result, nitrogen is going to get dissolved in your blood. Although nitrogen is practically insoluble, but when you dive deep inside the water, the pressure is going to be so humongous that it's going to push this nitrogen inside the blood and it's going to get dissolved. If you come back up quickly, this force that made this nitrogen to dissolve inside the blood is going to be disappeared. And as you come up, nitrogen is going to get out of your blood and it's going to create bubbles. And as a result, it's going to block your blood vessels. That's why it's going to create what's called decompression sickness. Many vessels, many boats, inside the vessel, inside the boat, there's a hyperbaric chamber that put this diver inside this chamber, and that chamber is going to decrease the pressure slowly, so nitrogen is going to come up out of your blood slowly and you can exhaust the nitrogen. So as a result, you're not going to release so much nitrogen inside the blood and blocking the blood vessels. So my point is that to dissolve a gas in the fluid, you have to consider solubility and the pressure. Let's take a look at the example. Let's say in this container, here is the blood. This is blood. And I'm trying to dissolve oxygen inside this blood. If I'm using 1 millimeter of mercury pressure, how much of this oxygen I can dissolve here? Well, the answer is we can dissolve 0.003 ml of oxygen inside this blood. Instead of 1 millimeter, if I change it to 10 millimeter of mercury, I can do 10 times more. So the answer would be 0.03 ml. And if I increase it by 100 millimeter of mercury, then I can dissolve 0.3 ml of oxygen inside the blood. What is my normal partial pressure of oxygen inside the blood? The normal partial pressure is 100 millimeter of mercury. In other words, in a normal pressure of the oxygen, you have 0.3 ml oxygen for 100 ml of the blood as a dissolved oxygen. So, in the pressure of 100 millimeters of mercury, you can dissolve 0.3 ml of oxygen in 100 ml of your blood. So, how much blood do I have? I have 5 liters of blood, correct? Or 5,000 ml of the blood. For every 100 ml, I can dissolve 0.3. So, therefore, 5,000 is composed of 50 deciliter, so 50 times 0.3 ml, that would be 15 ml. I can dissolve 15 ml of oxygen in my total blood. We need an average around 250 ml of oxygen to meet the demand. As you can see, 15 ml is not even close enough to meet this demand. So what do we have to do to carry more oxygen? Therefore, we have to use another protein called hemoglobin. As you know, hemoglobin also is going to carry oxygen. Let's see how hemoglobin is going to help us. 1 gram of hemoglobin can carry 1.34 ml of oxygen. How much hemoglobin do we have? We have, let's say, 15 gram of hemoglobin. So therefore, 15 times 1.34 would be the total amount of oxygen I can carry with my hemoglobin. That is around 20 ml. 20 ml per what? Again, per 100 ml of blood. So I can carry 20 ml of oxygen in every 100 ml of the blood. Think about it. Hemoglobin, as we mentioned before, can carry 4 oxygen. Here, 4 oxygen. If I put oxygen to every seat here, I can carry 20 ml. But normally, my hemoglobin is not 100% occupied. Normally, out of 100 seats, only 97% is being occupied. That means my 20 ml is based on 100% occupation. Since I cannot occupy every seat, only 97% is being occupied, so I have to times 90 by 0.97 because it's only 97%. The answer is 19.4 ml I can carry by 100 ml of blood. So I can only carry 19.4 ml per 100 ml of the blood. If I have 100 seats in a bus, I can carry 100 passengers. However, if I leave 3 seats open and I say I only carry 97 passengers, then my capacity is not 100, is 97, although I have 100 seats. If I put oxygen in every seat of hemoglobin, I can carry 20 ml of oxygen, but is not 100% occupied. Only 97 seats can be taken, not 100 seats. So therefore, my total capacity of carrying oxygen is not 20 ml, it's 20 ml times 97%. 19.4 ml of oxygen I can carry for every 100 ml of the blood, not 20. If you now think about it, since we have 5,000 ml of the blood, then the total amount that I can carry would be 50 times 19.4. That's for total amount of oxygen I can carry by hemoglobin. And that is going to give me 970 ml of oxygen I can carry in my total blood. Now I can meet my demand. The last thing I want to tell you is the idea of oxygen content. What is oxygen content? Oxygen content is a total amount of oxygen you can carry in 100 ml of your blood. Not in the total blood, but 100 ml of your blood. What's the total amount of oxygen you can carry in 100 ml of your blood? Well, we mentioned a few minutes ago that we can carry oxygen attached to hemoglobin, 19.4 ml of oxygen in 100 ml of the blood. We can also carry oxygen in the dissolved form, and that is 0.3 ml of oxygen in 100 ml of the blood. Therefore, in total, I can carry 19.7 ml of oxygen in 100 ml of the blood. Now, instead of saying 19.7 ml of oxygen in 100 ml of the blood, we say volume percent. Volume percent is how much oxygen you can carry in 100 ml of the blood. Let's say we have a patient that his PaO2 is 60 milliliter of mercury and the saturation is 90%. His hemoglobin is 14. I want to know his blood oxygen content. Again, blood oxygen content is composed of 2 segments. The oxygen dissolved in the blood and oxygen attached to hemoglobin. So let's see. We said for every milliliter of mercury, I can carry 0.003 ml. Now I have 60 milliliter of mercury, so I have to times by 60 to see how much I can dissolve in the blood. For every gram of hemoglobin, I can carry 1.34. I have 14 gram, so it must be 14 times 1.34. And remember, this is for 100% occupation. The question says only 90% is occupied, so I have to times by 0.9 because not every seat is taken. Here says only 90% of the seats are taken, not 100%. So therefore, I carry 1.34 gram of oxygen per 1 gram of hemoglobin. Since I have 14 gram, I have to times by 14. And since only 90% is occupied, I'm going to times by 0.9. So this much of oxygen can be carried by hemoglobin. And my oxygen content, which is a combination of these two, I have to add them up. The answer would be 17.1 milliliter of oxygen per deciliter. Since we said we have two different forms of oxygen to be carried in the blood, one in the form of dissolved oxygen, one in the form attached to hemoglobin. Remember, attached oxygen to hemoglobin does not create any partial pressure. The partial pressure of oxygen comes from dissolved oxygen. So let's say this is your alveolus, and here's your blood vessels. Air is going to come inside the alveolus. Here's the oxygen, and blood is going through. This is my pulmonary artery. Blood is going to get the oxygen and it's going to turn into a pulmonary vein, and finally it's going to go to your heart. So when the oxygen comes here, oxygen is going to get to the blood. For this oxygen to get to the blood, we have to have a difference in the pressure. The pressure of oxygen here must be higher than this one to come in. When the oxygen gets dissolved inside the blood, my PaO2 inside the blood is going to go up. And if it's going to go up, at one point, the pressure here and pressure here will be equal, and oxygen doesn't want to come to the blood anymore. We have to make sure that this oxygen keep coming in. What we have to do to make sure this gradient is going to stay the same? The answer is, as soon as oxygen is going to come to the blood and is going to increase PaO2, that is going to give the oxygen to hemoglobin. As a result, my PaO2 is not going to go up that much. As a result, there's always gradient for oxygen to come inside the blood. Let me repeat this one more time to make sure you understand. Oxygen is going to come from the alveolus to the blood. Why? Because of difference in the pressure. If the pressure of oxygen here and the pressure of oxygen here become equal, there is no need for oxygen to come in. So when the oxygen comes in and oxygen is going to get dissolved inside the blood, the PaO2 is going to increase. And imagine if the PaO2 is going to increase to the point that the pressure here and here becomes equal, then the oxygen diffusion is going to stop. We don't want oxygen diffusion to stop, do you? We need oxygen. So what we have to do is this. As soon as oxygen is going to come to the blood and PaO2 increases, this PaO2 is going to transfer this oxygen to hemoglobin. As a result, the PaO2 is not going to go up high enough to stop this diffusion. That is really important. So if I ask you, what causes this oxygen attached to hemoglobin? The answer is PaO2. PaO2 is the one that gives this oxygen to hemoglobin and makes hemoglobin to get loaded with oxygen. We have 4 seats for oxygen in hemoglobin, just like this. If hemoglobin doesn't have oxygen, it's called deoxyhemoglobin. When one oxygen is attached to the hemoglobin, the affinity of hemoglobin increases for second oxygen. Hemoglobin is going to say, okay, give me the other oxygen. When the second oxygen sits here, the affinity is going to increase even higher for the third one. And when the third one attaches, the affinity is going to go very high and attach the fourth one. This is called positive cooperativity. They cooperate with each other and increase the affinity of oxygen for hemoglobin. Have you ever asked yourself, how come hemoglobin comes to the lung and grab the oxygen, and this hemoglobin is going to go to the tissue and let this oxygen go? Because you want to grab the oxygen from the lung and carry it to the tissue and give it to the tissue. But how does hemoglobin know? I have to come here and grab the oxygen, and then I have to go to the tissue and let the oxygen go. The answer is, hemoglobin doesn't know. Hemoglobin is going to come to the lung right here, and because the pressure of oxygen here is higher and oxygen is coming in, oxygen is going to get attached to hemoglobin, and as soon as oxygen is going to get attached to hemoglobin, the affinity for the third and fourth one is going to go up. And when this hemoglobin goes to the tissue, the pressure of oxygen decreases from 100 to 40 by the vein. Then oxygen is going to get detached from hemoglobin. And remember, it is PaO2 that attaches oxygen to hemoglobin. As a result, when by the tissue PaO2 goes down, there is less force to attach oxygen to hemoglobin. That means the affinity for oxygen decreases and less oxygen is going to attach to hemoglobin. That's the reason that the hemoglobin is going to let the oxygen go, because PaO2 is going to come down. As a result, the affinity of hemoglobin for oxygen also is going to decrease.